and you know, he's
Wait, just ignore us and film whatever you want to. Go ahead, Freddie.
At any rate, so you have two end members, right? One is you have zero velocity, in which case it's totally diffusion controlled. You maximize your diffusive fractionation. The other alternative is that you have some very high velocity. It's probably unrealistic for the deep subsurface, but okay, let's go ahead and assume it anyway. In that case, you're not going to turn to zero your diffusive component, but it's going to be very small, and essentially you're going to have a virtually non-fractionating
Well,
transport.
I'd restate that, because remember, diffusion has two ways of coming out in these kinds of processes. One is a direct contribution, which, if the Peclet number is very large, becomes unimportant, period. Fractionation is unimportant. But a second part is buried in the mechanical dispersion that is in these processes. Underlying that is diffusion. I mean, it's still in
No,
there.
that's right. No, it's in there. And you
So what would it do to mechanical dispersion? I've never asked that question.
what do you mean by it?
Well, diffusion. If you go back and look at
Right.
fundamental
Yeah.
explanatory models of dispersion,
Right.
in mechanical dispersion models, like some of Jacob Beer's work, Beer and Bachmach and others, you'll see that those models, Safman and others, depend on the diffusion coefficient, because it's what kills concentration gradients at the pore level. And so you could ask yourself, if that diffusion coefficient leads to a fractionation of dispersion, which I've never heard of, but could be there.
Yeah, it is.
That could be interesting.
Yeah.
So even at high speed, not for the reason you're talking about, but for the second reason, you could have a fractionation effect. But let's assume it's negligible. It probably is. Let's assume it's negligible. So your second model is just to go up there and just take whatever that flux is at the bottom of the aqueduct and not even bother to model the thing below it. Because your bookends are, don't bother with the aquifer below. The other bookend is, assume it's diffusion only.
Yeah. Well, I mean, I don't see any issue in how to deal with these aquifers. I mean, that's fairly trivial. But what's bothering me here is how to deal with what's happening in the fractures, okay? Because in reality, if you have sparse fractures like I've drawn it here, it's not a 1D system, right? It's inherently a 2D system.
Well, if you you can calculate how time constants for these shapes, and I would do it not with a first order model, but with an actual cubic or rectangular model for a matrix. You can calculate at what frequency of fractures you need to model them explicitly, as opposed to treat them with some kind of double porosity approach.
And how do you calculate that?
The time constant? Well, it's pretty